So hello everybody. I'm Hendrik Schatz. I'm from Michigan State University, and I'm the director of the Joint Institute for Nuclear Astrophysics, and I really want to welcome you to the kickoff of the Nuclear Astrophysics lecture series that we organized in JINA, that's what we call the Joint Institute for Nuclear Astrophysics. JINA is a collaborative research network. Includes about 350 scientists, 30 institutions, some abroad. So it's a very large network. About a little bit more than 100 participants are students. So, and there are also many undergrads participating in research. And the idea is to bring together astronomers and nuclear physicists, not usually working together, and figure out together the big question of the origin of the elements. So basically, if you look around, you probably see a computer. It's made of elements like carbon, oxygen, and heavy elements. And we just want to understand, how did nature create these? And the lecture series, and to do that, we use accelerators. We have a very large accelerator facility here at MSU, and we will get even a bigger one in about 1 or 2 years, currently under construction, to do the nuclear physics part. But JINA also uses accelerators underground, actually the deepest underground accelerator in the US, about a mile underground. We're also using largest telescopes, the largest computers. We're using gravitational wave detectors, and this all has to come together. And so this lecture series was developed in collaboration with a number of JINA institutions, including some smaller schools as well, and including some minority serving institutions. And the goal is to introduce this cutting science to undergrad students. I hope there's some students here, and I hope you're excited about this. And of course, others that may be interested. No prior knowledge is required. This science sounds scary, but the idea here is to really start from scratch, and also take advantage of the fact that the very broad range of physics needs to come together in this particular area of cutting-edge science. That includes optics, nuclear physics, solid-state physics, plasma physics, atomic physics. So we hope that you can see how some of the different pieces of physics come together that you've maybe been exposed to in some of the classes, how they come together and is applied to cutting-edge science. We hope we can share our excitement about this field and this area. And we also hope you learn about research and grad education, grad school, and careers in physics. And so today we have the first lecture by Remco Zegers. He's a colleague here at MSU. He's a professor. He got his PhD actually in the Netherlands, in Groningen. I'm probably pronouncing it wrong. He also worked in Japan, and he's now here at Michigan State University, and he's an experimentalist. He carries out experiments throughout nuclear processes and stellar explosions that involve the weak force, exciting things like neutrinos. He's also a fellow of the American Physical Society. He served as associate director of experimental nuclear science here in the lab. And he does a lot of things. He's also currently the graduate program director at the Department of Physics and Astronomy. So he's the perfect person to ask questions about grad school. And I think I'll tell you a little bit about that too in this first lecture. So let's kick it off with Remco Zegers. We'll collect questions throughout the presentations in the chat. So if you don't want to ask in voice at the end, you can also write your questions, if you're more comfortable with that, into the chat. And then at the end, we'll do a mix of questions from the chat and live questions from the audience. Okay, so let's fire away.
All right, thank you, Hendrik. Can you hear me? Yes.
Okay, very good. Thank you all for joining. I'm very excited to be here and give the first lecture in this series. I was super excited about the poster. It's really cool. So I'm very excited to be here. So I'm going to give an overview about multi-messenger signals from astrophysical phenomena. And this is going to be extremely broad and not very deep. And I'm certainly not an expert in all the things I'm going to talk about. So if I say something stupid, I hope somebody will correct me. But the idea is to give an overview of the big picture, and then in the end, I will focus a little bit more on the nuclear astrophysics side of things, and basically as a segue into the following lectures. As Hendrik mentioned, I'm also the graduate program director here, and I have a few slides at the end about applying to graduate school if you're interested in that as well. So let me start. So probably you might have seen a picture like this. This is a description of basically the history of the universe. And on the left side right here is the Big Bang. This is where everything started, at least that's what we currently think. And the universe we know is probably about 13.8 billion years old. And right at the start, right in the beginning of the Big Bang, there wasn't too much. The universe was actually very small, as I will show on the next slide. And then over time, different stages appeared. Different types of particles were produced. First, there were quarks, and then nucleons like protons and neutrons. And through various mechanisms, nuclei started to be formed. So the more heavier systems, first deuterons, and then helium and tritons, etc. And so these are all heavier elements that were created. And then slowly, these elements formed clusters and nuclei could be formed. And this often happens in stars. So the star formation, which happens relatively recently in the age of the universe, at least the younger universes, younger stars, they were formed, they are basically serving as hosts for systems that can make a nuclei. So, so I'm going to talk a little bit about the Big Bang, and then just to give a big overview. Now, you might wonder where the Big Bang model is coming from, and the main theoretical foundations are through the general theory of relativity and the cosmological principle. And maybe you have heard a little bit about relativity in one of your physics classes. This is, of course, made famous by Albert Einstein, who really developed this in the beginning. And the cosmological principle basically states that the universe is roughly the same everywhere and in every direction. And so that means that the universe is isotropic and homogeneous. And this homogeneity and isotropy have important consequences, because it means that the observational evidence is available to observers at different locations in the universe. And the same observational evidence is available by looking at any direction in the universe. And this principle also implies that the laws of physics are the same everywhere, and that the fundamental constants are the same everywhere. If that were not the case, then things would be very difficult to figure out. And finally, and this is one of the grounding principles of the Big Bang theory, is that the cosmological principle implies that all parts of space were connected at some point in time. And so a famous researcher, Alexander Friedman, used these foundations to make a model of the evolution of the universe. And the solutions of those foundations basically suggest that the universe originated in a Big Bang, and it is a very hot and dense matter, and has been expanding in size ever since. So here's a very brief 2-slide version of the evolution of the universe, and there's a little bit of speculation here because there's we don't know everything. So in the very beginning, so I put here on the left-hand side some time. So this ranges from 0 to 10 to the minus 43 seconds. So that's really right at the start of the Big Bang. We have no clue what really happened, right? We have no understanding what happened in that initial period. And all the fundamental forces that we are aware of, they were all unified into one force. And the universe was very small, smaller than 10 to the minus 52 meters, and it was very hot. The temperature was 10 to the 30th Kelvin, so extremely hot. And so since that beginning, the universe starts to expand. So you can see that in these later stages, the size increases, from 10 to the minus 30 meter, 10 to the minus 1 meter, up to larger distances. And the temperature goes down from 10 to the 30th Kelvin, and after a few hundred seconds, about 10 to the 9 Kelvin. And so initially, just after the Big Bang, the gravitational force separates from the other forces. And shortly thereafter, the quarks and leptons start to form. So these are fundamental particles that are the building blocks of matter. And the strong force is separating from the other forces. And then after another little while, protons and neutrons start to form. And the weak and electromagnetic forces start to separate. So at that time, the universe is maybe about 1,000 meters in size. And then shortly thereafter, so up to a few hundred seconds, this is where the first nucleosynthesis starts, so where the first nuclei are being formed, and these would be deuterons. And once you have deuterons, you can start to make heavier elements as well. So then the time scale changes rapidly. So between 180 seconds and about 300,000 years, this is where light nuclei start to form, and I'll show a little bit more about that later. And then up to maybe 1 billion years, this is where the formation of stars and galaxies happens. And the temperature becomes really cold. It's only 10 Kelvin at that point. And so from that period onwards until now, this is where we have stellar evolution and, of course, the formation of life. And the temperature is maybe about 3 Kelvin. So it gets really cold in the universe. So that's a very brief overview of the universe and the Big Bang model as we currently understand it. So what about the birth of stars? So how does that happen? So once you have clouds of hydrogen and helium, they can clump together in nebula. And once the density increases, the nebula can collapse due to gravity. The density becomes high, and then the core can heat up, resulting in hydrogen to fuse. So this is when the star is basically born. And then what happens with that star really depends on the initial mass. So the life cycle of the star depends on the initial mass. So if the mass of the star is very light, fusion cannot really happen, and you create a brown dwarf. And if the mass is really high, about 200 solar masses, this becomes unstable as too much energy is produced. So in between those two ranges, you can make a wide variety of different types of stars. Now, this is a nice plot. I really like this plot. This plot shows the luminosity on the y-axis versus the surface temperature of the stars. And you can see that there is a band here, which is called the main sequence. And almost all the stars initiate their existence on what is called this main sequence. So there's a strong correlation between the luminosity and the surface temperature of the stars. And all these stars undergo hydrogen and helium fusion in their cores. And the lifetime that the star remains on this main sequence depends on how heavy they are. Heavier stars live shorter as they burn faster due to the higher temperatures. And so again, here I give some examples of some stars. If you have, for example, if you have a very heavy star, maybe 10 times the mass of the sun, it only lives about 20 million years or so. If you have a much lighter star, they can live for a much longer period of time. Okay, and so this is sort of an overview of the different stars that we have in the universe. So how do we learn about stars? And this is really the first messenger, and this is the oldest one. You can just look at them, right? You can just look at the light from the stars. And really the interesting thing about looking at stars is that you look back in time. The speed of light is constant. It's about 3 times 10 to the 8 meter per second. And so it takes time for the light to travel here. And so if you look at very distant stars, you basically are looking back in time. And so this allows us to look back towards the Big Bang, right? Because you're looking back in time. And you probably have heard of the Hubble telescope. It's a very famous telescope, which produces wonderful images of the universe. And on this picture on the right here, so this is Hubble right here. And so Hubble is looking back in time up to about this point right here. Okay? It can see some of the oldest galaxies that are formed and some of the oldest stars, and I'll show a few examples later. And there's a new telescope, James Webb, which will be able to go even further. It can go much further back in the past, and we can even learn more about the universe. Now, you might say that you can just look at the light, but it's actually quite complicated. One important aspect is that because these objects are moving, the light is Doppler shifted. And you probably heard about the Doppler effect. And if not, I can explain in more detail. But basically, it boils down to the fact that the wavelength of the light is shifted in the infrared because of the high velocity relative to our movement. And so this telescope must be sensitive to the infrared light. And the further you are away, the shift of the light towards the infrared becomes stronger. So these telescopes, like Hubble and James Webb, and of course many other telescopes, they have to be able to look at the infrared light. So this is really cool that you can look back in time because you can observe very old galaxies. And I just picked an example here, a fairly recent one. This is from September 2019, where some of the oldest observed galaxies were discovered by using Subaru, Keck, and Gemini telescopes. And this picture on the right-hand side kind of zooms in on some of these clusters, some of these galaxies. And so they are extremely far away, and they are about 13 billion years old. And the observation of these very old galaxies and stars reveals a lot about the collective chemical evolution of the universe. How did the formation of stars happen? And these old galaxies are relatively small compared to the newer ones. There's no spirals or ellipticals like our own galaxy. And this probably indicates that these are very high rates of star formation, and that there are also collisions between these galaxies. So you can really look back in time pretty far. And I understand that this is the current record holder. It's called JINA-CEE 11. They could pick a nicer name for it. And this is a picture from Hubble. This one is about 13.4 billion years old, which is actually quite surprising because we think that the universe is about 13.8 billion years old. And so this particular galaxy was created fairly quickly after that. Right? So this is a nice picture which shows on the bottom side right here that billions of years ago, so this is present day, and this is the Big Bang, this is when everything started. And so this galaxy is sitting somewhere on this timeline. So this is quite surprising. The previous record holder is also indicated on this graph, and it's shown right here. So there are other things that we can look at. This is a second type of messenger. We can look at the microwave background radiation. And one of the probes that was used for that is the Wilkinson Microwave Anisotropy Probe, WMAP. And so this probe measures small variations in the temperature of the cosmic microwave background radiation, which is really the oldest light in the universe. And this is another picture of this Big Bang expansion. The Big Bang is starting right at the left-hand side here. And so this cosmic microwave background radiation was created right after the Big Bang. And so this radiation is left over after the temperature dropped below about 3000 Kelvin. And actually now it's about 2.7 Kelvin due to this Doppler shift. And one finding from this WMAP probe was that the variations, if you look around in the universe in this background radiation, is extremely small. And so that's very interesting. It shows you that the universe is quite homogeneous and flat. And so this WMAP indicates that the universe is flat within about 1% margin of error. And there is a follow-up mission, Planck, which looked at this in more detail, but it basically confirmed the earlier results from WMAP. So this kind of measurement can tell you something about the large-scale structure of the universe. So before I talk about the next messenger, I have to talk a little bit about relativity and the curvature of space-time. And so this is underlying the general theory of relativity, but I just try to give here some of the basic principles. So rather than describing the motion of objects affected by the gravitational force, one can describe the motion as being affected by the curvature of space-time due to the influence of heavy objects. And so you have pictures like this one here on the right, where you have an object, say the sun or some other astrophysical phenomena, and objects that move around it are attracted to it because this heavy object makes a dent in the curvature of space and time. And this space-time curvature tells matter how to move, and there's a nice example at the bottom here. So this is the sun, and this is the Earth, and there's light coming from different stars. That light gets affected. Its movement gets affected due to the gravity induced by the sun, or by the curvature of space-time. And so that underlies the general theory of relativity. And this sounds all quite alien, but you can actually measure this. And I picked just one example. I thought that this one is very cute. So this was an experiment that was done in the 60s. And this measurement that I show on the right-hand side there is from 1917. What they did is they looked at light traveling from Venus to the Earth. So that, oops, sorry. If this is Venus right here, and this is the Earth, light can travel from Venus to Earth, and you can send signals to Venus. In this case, they actually send a signal towards Venus and then have it bounce back towards Earth. If the sun is not in between Venus and Earth, then that signal can move unperturbed. But if the sun is just in between Earth and Venus, then that path will be disturbed by this curvature of space-time. And so the longer path causes a time delay for the light traveling close to the sun. And so, as I mentioned, this effect was first measured by sending a radar wave to Venus, where it was reflected back to Earth. And so when it was in the superior conjunction, so that's close to this situation right here, when the Earth and Venus are on opposite side of the sun, the signal passed near the sun and experienced a time delay of about 200 microseconds. And that's what you see right here. So where this peak is where the superior conjunction is. And the y-axis here is the excess delay, so the extra time that it takes for the signal to reach Earth. And so you can see this nice peak. And so this is a very nice example of this curvature of space-time. And this brings us to the third messenger, which is probably the most recent one. This is looking at gravitational waves. So similar to an oscillating or accelerating charge producing electromagnetic waves, oscillating and accelerating masses should produce gravitational waves. And as gravitational waves move through space-time, they cause small waves which potentially can be detected. And so what they do is they try to measure this gravitational wave moving through space-time, and they try to measure the strain, which is a measure of how much a gravitational wave distorted space-time, which is equal to the distance between two objects divided by the original distance. So you see if something is fluctuating. And there's different, the gravitational wave spectrum has different frequencies, just like light has different frequencies. And so you can look at different types of objects that produce gravitational waves of different frequencies. And this picture on the bottom right here is an overview of the gravitational wave spectrum. So until recently, it was not possible to measure these gravitational waves, but this changed with the construction of LIGO, which is the Laser Interferometer Gravitational Wave Observatory. And it actually consists out of two sites, one at Hanford and one at Livingston, and this is shown right here. Each of these arms is about 4 kilometers long. And so LIGO uses the physical properties of light and of space itself to detect the gravitational waves. And there are also other gravitational wave observatories in the world, and some Italy and Germany. So how does it work? So I don't know if you have seen this in one of your physics classes, but it's based on the Michelson-Morley principle. It's just much bigger. So the right-hand side here shows basically the Michelson-Morley setup. We have a laser coming from the left, and it passes, it gets split here. Some of the light goes to the top, and then it's sent backward, and some of it goes through this mirror, and goes over here and then turns back. And so the mirrors reflect the light back the way it came. The beam splitter combines the two beams back into one, sending it to a detector. And this detector is sitting right here. And so LIGO carefully tunes the length of these detector arms, so these two arms right here, so that the light of the arms undergoes destructive interference, so that the light just cancels out and you see no signal here. And so if an arm length changes slightly because a gravitational wave passes by, then the difference in the length will introduce a small difference in the phase between the beams from the two different arms. And that's how you can detect a gravitational wave. And so the waves that would have canceled each other at the beam splitter will now travel slightly different path lengths and end up producing some light at the detector system. That's the basic principle of these interferometers. And so it's very exciting when these signals were first discovered. And so a very famous one is the neutron-star merger from August 17, 2017, which was observed by LIGO and Virgo. And because it was possible to approximately tell where the merger took place from these measurements, I have a picture on that in one of the following slides, a variety of other telescopes were used to accumulate additional information about the merger, for example, X-rays and visible light. And so this is a very good example of a multi-messenger event where you can get different pieces of information from different signals that you detect. And this was a very important for nuclear astrophysics, because it became clear that heavier elements than iron were produced in this merger, even though some of the details are still unclear. This is a screenshot from a picture in Nature where they talk about the identification of strontium in the merger of the two neutron stars. So this was extremely exciting. And so what happens with neutron stars and why do they merge? So neutron stars are remnants of supernovae, of stars that have exploded. And they're quite small. They only have a radius of about 10 kilometers and a mass of about 1.5 solar masses. And the whole star has a density that's close to that of atomic nuclei. So it's extremely dense. And it's very neutron rich, right? That's why it's called a neutron star. And a single neutron star by itself does not eject matter in space. However, when the two neutron stars merge, as shown on this little animation on the right here, you can have a spectacular event, and this is where nucleosynthesis can occur. So the two neutron stars circle in onto each other and eventually merge. And so this gravitational wave signal from this neutron star merger could be measured. And this is some of the data that was taken from the different interferometers. I like this picture on the left-hand side here. You see the neutron stars are spiraling in, and this induces this gravitational wave signal. And this goes faster and faster when they get close. And in the end, they merge together, and then it rings down and the signal stops. And so the interferometers could measure this signal, which was very exciting. And since both of them could measure it and they are nicely overlapping, it made it much easier to separate it from noise in the signal. And as I mentioned, you can combine the results from the different interferometers, and you can localize the location in space where the event took place. Not very precisely, but precise enough for other telescopes to be used and learn about the event that just happened. And so this is, of course, very important because then we can get different pieces of information. Now, there are other messengers. So a very well-known messenger is cosmic rays. Cosmic rays are particles that bombard Earth from outer space. And most primary cosmic rays, prior to entering the Earth atmosphere, these are protons, maybe alpha particles, and maybe some heavier nuclei. And a small fraction of them is electrons as well. There's also a small fraction of them that are antiparticles, like positrons or antiprotons. And these particles interact in the Earth atmosphere, and they create showers of secondary particles. At the left-hand side here is an image of what could happen. So you have a particle that comes in and it interacts in the atmosphere, and it creates many different types of particles. And some of these particles can be very energetic. The most energetic cosmic ray that is observed to date is about 3 × 10⁻20th electron volt, which is about 51 joule. So basically, one of these tiny particles had the same kinetic energy of a baseball at about 60 miles per hour. And so it's extremely energetic. Most cosmic rays have an energy, a kinetic energy somewhere between 10 MeV and 10 GeV. Now, these cosmic rays come from a wide variety of sources, so you can learn about different things. And so people have built observatories for these cosmic rays. One famous one is the Pierre Auger Detector Observatory in Argentina. And they basically, throughout the field, it's a little bit hard to see in these pictures, but they have these little huts right here that all try to measure some of these particles from the shower. And if they do that for several particles, they can reconstruct and they can learn about the primary cosmic rays. So neutrinos are also a cosmic ray particle, but they're a little bit different. So I treated them separately. So I call them messenger 5. So I don't know if everybody has learned what neutrinos are, but neutrinos are leptons. They appear to have no internal structure and are point-like and referred to as elementary. And each lepton or neutrino has an associated antiparticle. And neutrinos are very interesting. In the standard model of physics, they are predicted not to have mass, but we know that they have mass. So this, the fact that neutrinos have mass actually tells us that the standard model of physics is not complete. And neutrinos are produced in reactions mediated by the weak nuclear force, for example, beta decays and electron captures. And that's important for astrophysics because these things take place in stars, for example. So neutrinos can make it to Earth and we can learn something about stars. So, so neutrinos are heavily investigated because of the special situation in the standard model. And neutrinos are very complicated. They come in 3 flavors, tau, mu, and electron. And they're complex mixtures of their mass eigenstates. And so this makes them very difficult to study. And because of these mixtures, neutrinos can oscillate from one flavor to another. And this is necessary to explain the solar neutrino problem, which I will just mention in the next slide. So the mass differences between the different neutrinos is known, but we don't know the hierarchy. So if you look at this picture on the right here, it shows the 3 different mass eigenstates, and the colors indicate the flavor states. So this is a very complicated picture. But the main thing to take away from this is that we don't actually know which mass eigenstate has what mass. And so this hierarchy is something that researchers are still working hard on. Neutrinos might be their own antiparticle, we don't know, but if that's true, it would have implications for the imbalance between matter and antimatter in the universe. And this is another topic where a lot of research is being carried out as well. So a very famous detector to measure neutrinos is the snow detector. So neutrinos interact through the weak force, so they're very, very difficult to detect. And the flux of neutrinos on Earth is about 7 × 10⁻⁻⁻ per second per square centimeter. So while we are listening to this lecture, we're getting bombarded with neutrinos left and right, and we don't notice it because they don't interact with us at all, which is good. And so if you want to detect these particles, you need a huge detector. And this is a diagram from the snow detector, which is sitting deep in the Earth. This is to protect it from other radiation, cosmic rays that might disturb the signals. And this snow detector was very important to understand the production of neutrinos from the sun. So we could actually learn about the properties of the sun by measuring the neutrinos. And they did an experiment where they filled this detector with heavy water and then looked at the signals that were produced. And through this experiment, which is very famous, it became possible to study the contribution from each flavor of neutrinos that was coming from the sun. And it demonstrated that neutrinos have mass and oscillate between the flavor states. It's a very, very famous experiment. There are new neutrino observatories. I think this is the coolest one, literally, because it's sitting on the South Pole. And it has detectors that are placed in ice. And so it's called IceCube. And this is a layout of that detector. It's used, this is about 2,500 meters, so that's the depth. And this is where the detectors are sitting at the bottom right here. And so people are using this system to look at neutrinos. And what they see is when there is an event, they see particles or hits in the detectors that are sitting under the ground here. And from that, they can reconstruct what happened in each event. So this is a very active area of research. And for example, here at Michigan State University, we have several people that are working on this ice cube project. So as I mentioned, neutrinos can come from stars, which make them very interesting to use to learn something about stars. And I don't have time to discuss all the various ways that stars can cease to exist. Unfortunately, there are many ways. But if you look at the heaviest stars, so if the star is larger than 5 solar masses, then the hydrogen burning happens relatively rapidly. And the star starts to move off this main sequence after about 100 million years. So this is this main sequence that I mentioned earlier. And helium fusion starts while the outer layers of the stars expand and the temperature drops, and the luminosity is a consequence rather constant. And then depending on the core temperature, fusion can proceed and create heavy elements up to iron 56. And at that point, fusion can no longer continue because no more energy is created. And so you see some examples of these stars here. Here's Betelgeuse. This is a red supergiant. It has a large radius that has expanded, for example. So, some of these heavy stars can evolve into what we call core collapse supernovae. And so this is just a little diagram of that. So on the top left right here, this is the situation where the stars produce in fusion heat, and there's an electron pressure, so there are electrons in here, free electrons, that keep the stars from collapsing onto itself. So the gravity is trying to pull material in, but the fusion heat and electron pressure is working against that. And once the fusion stops inside the core because you run out of the fuel, you've made too much iron, then this gravity starts to win, and the pressure becomes high. So then the core starts to contract, and only this electron pressure is really able to balance it a little bit until it's no longer possible and the core collapse sets in. So when that happens, the core collapses, and then there is a bounce because the density becomes too high, and there's a shock wave that is produced. It is believed that that shock wave is not necessarily enough to explode the star, but there's also neutrinos that are produced, and these can re-energize this shock wave. And so then the star explodes. And so in this event, a lot of neutrinos are produced, partially from electron captures on the heavy nuclei inside the star. And you can try to measure those. I like this animation here. This is from a supernova. It just shows you how powerful this supernova explosion is. It's almost as bright as the entire galaxy that the supernova is sitting in. So you don't want to be nearby if that happens. So there's a lot of power. So the star explodes with 10 to the 45 watt, which is more than 20 orders of magnitude more than about 20 orders of magnitude more than the power that our sun gives. And these supernovae can be detected. You can of course look at the light. So there's an image right here on the right, which shows an example of a supernova. This is a very famous one, 9087A. And from this particular explosion, they were also able to measure neutrinos in these neutrino detectors. Not many, but there are a few. And this plot on the bottom here shows the energy of the neutrinos versus time. And so this gives you some additional insight in what happened during the core collapse supernovae. So like the case of the gravitational wave, there's multiple types of signals that you can use simultaneously to better understand what is going on during the core collapse supernova. All right, so let me change gears a little bit. To understand what makes this all happen, we really have to look at the smallest elements inside a star, the nuclei that are there. And probably you're familiar with the elements like carbon, oxygen, nitrogen, etc. And nuclear physicists usually look at these in what we call a chart of the nuclei. And this is shown right here. So on the y-axis right here, this gives you the proton number. And on the x-axis right here, it gives you the neutron number. So as an example, you can pick carbon-12 right here. This is 6 protons and 6 neutrons. And then just next to it is carbon-13, which has 1 neutron in addition to it. These are both stable, carbon-12 and carbon-13. You can find them on Earth, and carbon-12 is the most prevalent. But then the next one, carbon-14, is not stable. It will decay. It lives for about 5,700 years. That's why it's used for carbon dating, which you might have heard about. Now, if you add additional neutrons, these nuclei will live shorter and shorter. For example, carbon-20 only lives for about 0.01 seconds. So it lives only for a very short amount of time, but still these nuclei can be very important inside stars. So if you zoom out a little bit, so this is the full chart of the nuclei. It's a little confusing, but the protons are on the z-axis here and the neutrons are at the y-axis. And so if you look at this chart of nuclei, only a few of these isotopes are stable, and they are highlighted in black in this graph. And the other isotopes, they will decay away, beta decay or fission or other decay modes. And the further you are away, this is shown on the right-hand side, the shorter that time period is, the lifetime is shorter. So how do we make these nuclei inside the universe? So the lightest element, as I mentioned earlier, I made in Big Bang nucleosynthesis, which is about the first 10,000 seconds of the universe, create these light elements, from the protons, deuterons, triton, helium-3, the alpha particle, helium-4, and also lithium-7 and beryllium-7. And this is fairly well understood. There's still some open questions, but this network is quite well understood. And so this happens early on in the age of the universe. And on the right-hand side, I show some calculations with different models based on this reaction network. So how do the heavy elements, how are they produced? This is what Hendrik was referring to. Where are they made? And so there's many things that we don't know yet. And so we also don't know where they are made necessarily. And these two questions are strongly coupled. As the boundary conditions for certain nuclear reactions to take place is tightly connected to the density and temperature inside the astrophysical phenomena that they take place in. And so on the right-hand side here, there's a picture which has the chart of nuclei. And I think in the following lectures, you will see much more detail of this. And inside this chart of the nuclei, there are different reaction paths that indicate different ways to create nuclei. And for example, a very famous one is this R process, this is the rapid neutron capture process, which takes place involving many unstable nuclei, so very far away from the valley of stability, which are these black dots right here. So initially, these nuclei are produced, they're very unstable, and then they slowly decay towards the valley of stability. So to understand the creation of these particles, you need to understand these different reaction paths. And I'll show just one example right here. This is a movie that I believe Hendrik made some time ago in 2012. And this is a simulation of the rapid neutron capture process, which we believe the neutron star mergers are a site for. I'm just going to play this so we can start, and you can see there's the time and temperature. You can see different elements are being made. So again, this is protons on the y-axis and neutrons on the x-axis, and you can see that in this particular reaction path, you make very neutron-rich systems, very far away from the stable isotopes we find on Earth. It takes a little while. I'm going to let it run. You can see now it creates very heavy elements, and all the way up to the right here. So these are the heaviest elements. And so once they are created, they start to decay back towards the valley of stability, these black dots right here. And so these are isotopes that eventually can make planets. And so that's why you can find them on Earth. And so to understand this kind of reaction network, you need to know a lot of data. You need to know the properties of the nuclei and how they react. Otherwise, you cannot perform a simulation like this. So how do you study these relatively short-lived nuclei? And one way to do that is with the Facility for Rare Isotope Beams. That's what we're currently constructing on the campus of Michigan State University. And the basic idea is to use a beam of very heavy nuclei, such as uranium-238, and you shoot it at a production target. And when that happens, you create many different elements. And some of them are the most interesting short-lived ones that can also be found in exploding stars, for example. And so these are extremely interesting for nuclear astrophysics research. And then we use complex detector systems to study the properties of these nuclei and the reactions they induce. And so this is a little overview of the facility on the left here. Maybe in the following lectures, you'll see a little bit more about that. On the right-hand side is an overview of the nuclei that we hope we can produce at FRIP. So in this dark blue color, this is the isotopes that we currently know known to exist, that we know a little bit about. And at FRIT, we can more than double the known isotopes because we can produce them in the laboratory. And maybe after, with FRIT, we'll know about 80% of all the isotopes that can be made. So this is really exciting for nuclear astrophysics research. Currently, we're operating the National Superconducting Cyclotron Laboratory, and it does basically the same thing, but the beam is not as powerful that we have from FRIT. But this just gives you an overview. These are two cyclotrons. They create beams of particles. And in the case of NSCL, these particles travel at about 40% of the speed of light. And so you can shoot them at a target. There's a little production target. It's really just a thin foil. And you produce all kinds of elements. So again, this is the chart of isotopes, neutrons and protons, and you produce all kinds of stuff. And then we have a machine which we call a fragment separator, consists out of many magnets, which we can use to separate out the isotopes that we're most interested in. And in this particular example, we were interested in nickel-78. The experiment was focused on nickel-78. So they purified the beam to get rid of some of the stuff we didn't want. And so with this device, we have produced more than 1,000 rare isotope beams, of which 870 have been produced in various experiments at the laboratory. And many of them for the purpose of studying nuclear astrophysics. So that was my overview. So I covered a lot of areas without going into a lot of detail, but I hope this gives you a little bit of the taste, what we're trying to do and why it's so important to have different fields work together. So the exploration of the evolution of the stars and nuclear synthesis is really a multi-physics study, right? You need to do a lot of stuff. It requires astronomical observations, astrophysical modeling, physics input from a wide variety of subfields, almost anything you can think of, including microscopic nuclear and particle physics. And so it's kind of interesting to see that to understand the origin and the history and the fate of the universe, we must study science at the larger scale, right? We have to understand the whole universe, but we also have to understand science at the smaller scales, at the level of nuclei and even below that. And this is really an exciting time to be involved with this research because there's so many breakthrough discoveries, right? We had the gravitational waves, there's a lot of work in neutrino detection, there's new telescopes, and then there is the new facilities to study nuclei, such as the facility for rare isotope beams. So if you're interested, this is really a great time to get involved. And so with that, let me talk a little bit about graduate school. If you find this exciting or you find a different research area very exciting, doesn't really matter. There are many different cool things to do. I started out as a material scientist, and somewhere along the way, I converted to being a nuclear scientist. And both were great fields to enjoy. So if you're thinking about pursuing research or to pursue your PhD to work in a national lab or to do other things, I can talk a little bit about what you can do. So this is what the next few slides are about. And if you have other questions, you're always free to contact me. I can't cover so much material in this short amount of time. So when you consider graduate school, it's important to consider what your career goals are, right? You might want to go into industry, you might want to go to a national laboratory, you might want to go in academia or do teaching, and that you can do at various levels. You might want to go into science policy and join the government, for example. And when you take a PhD, you can go into any of these areas. We have students that graduate and they go in all of these, they go in all of these different areas. About 20% of the physics PhDs stay in academia. That's sort of the number. So that's a significant number, but certainly not the majority. And if you're thinking about careers, there's some great resources. If you're not a member of the APS, I encourage you to do that. They have great websites. I give some links here where you can look into careers. So say you have determined what you would like to do and what your passion is. How do you select the grad school? You know, what area and specialty should you study? And this depends on many different things. Do you want to do theory or experiment? Maybe you don't know. You want to try something out. What areas of physics are you interested in? You know, it can be anything: condensed matter, high energy, nuclear, atomic, biophysics, anything really. And so that's an important consideration. If you're interested in several areas, consider which you enjoy most and is best suiting for getting you to your career goal, right? If you have a clear goal in mind, what is the best program for you to follow? And you know, talk to mentors, anybody, professors, your RU advisor, if you have a chance to do an RU or any other type of research, and do research. I think this is the most important. But talking to mentors, I'll come back to that, is extremely important. And also, if you're very interested in a particular program or group, don't hesitate to reach out to the professor or the graduate program director, right? I get emails all the time from students who are interested in a certain type of research, and you know, I'm happy to answer those, and I'm sure other graduate program directors are as well. So how do you, you know, once you decide, okay, I really want to go to graduate school, how do you select one? Spend some time researching different schools. Don't just pick at random, right? Really look at what is available at the different schools. There's a lot of online resources, departmental web pages. There's searchable databases. But again, ask professors, bosses, mentors for recommendations of schools, and even specific thesis advisors. They might know what area of research might be strong at what university. And think how you perform best, right? That is also important for selecting a graduate school and eventually an advisor. You know, what do you want to do? Want to be very independent? Do you want to work in a world famous group? There's all kinds of considerations that go into selecting a graduate school. So as I mentioned, mentors are extremely important, and I think almost everybody who did a PhD talked to many people, many mentors, and so it's very important to find good mentors and a strong mentoring network. You know, most schools realize the importance of this, and they will assign you one. But I strongly encourage you to find several mentors. Different people have different perspectives, and I know sometimes students are a little afraid to ask people for advice, but my experience is that you will find that most people are very keen to talk about what excites them and what they are interested in. So you just have to reach out and people will start talking and giving you advice. There are also some resources like the APS National Mentoring Community, which facilitates and support mentoring between African American, Hispanic American, and Native American undergraduate physics students, and I provide the link here. So there's ways to get mentoring from APS through APS. Now, once you decide to apply, I made this slide very recently. I think these are the main components of an application, and I think that's very important. So if there's some of you who are planning to apply soon for graduate school for next year, I think these are some of the important areas to cover. Obviously, you want to talk about your academic performance, you know, your grade point average, you know, the department that you have worked in, research that you have done. Maybe you're on some publications, maybe, and of course, you need to submit letters of recommendation that can speak to your achievements as well. You know, when you look at programs, be sure to write about research goals that match to the department or the program. State the purpose, the breadth, and the depth of the research experience. You know, does it fit with what people at that school that you're applying to are doing? This is very important. So this is where you can show you that you've done some research into the program and that you think that this is an exciting place for you to be. And the next three bullets, people tend to forget, but they are very, very important, and they are becoming more important. You know, if you have done any kind of leadership roles, this could be academic, professional, or in the community, evidence of leadership potential or potential to make a distinctive professional or scholarly contribution is very important. If you have been the president of a club, you know, listed, everything there I think is very helpful. The other two bullets, contribution to a diverse educational community. This could be personal history and experience, or research goals, or the promotion of understanding among persons of different backgrounds and ideas. And again, if you have served in an organization or did work or outreach, this is something you should definitely list on your application. And another thing that graduate schools look at is the record of overcoming obstacles. And this could be almost anything. This could be social, economic, or personal. But it's typically something that's being asked and you should highlight. And I think it's important to cover as much as you can on these. Of course, if you haven't been in a leadership role, that's perfectly fine too, right? You cannot maybe have all of these elements, but try to cover these if you can. So finally, say you have submitted and you have gotten some offers. Where do you decide to go? You know, visit the place if you can, meet with the professors you might want to work with, speak with current undergraduates, current graduate students if you can. And again, talk to your mentors about your options. They can give you feedback as well. And you don't have to limit yourself to research areas where you already have some experience. You know, choose what you're most interested in and excited about. If you have done some research in one field, you can certainly swap fields at the graduate level. And maybe you want to try some different areas in the beginning of your graduate school just to see what you really like. Okay, that was it for me. I hope that was helpful. I'm happy, of course, to answer any questions about the presentation or about graduate school.
Thank you, Remco. Okay, we have time for questions, and I was hoping we could maybe start with some of the students asking questions. If you have any questions, I can't really see who's a student and who isn't, but won't believe you. If you have a question, I think you can just go and unmute yourself. This is not such a large group, so we can keep it a bit informal. Is there anybody who wants to ask? You can ask anything. Too many questions? Okay, well, this is difficult on Zoom.
Okay, let me start since nobody wants to participate. If the fate of the sun is the same as the fate of the universe, it's a basic question.
Well, actually, yeah, I did not cover this much. I had some slides on the fate of the universe, which is an interesting topic all by itself. So, so the sun is relatively light, right? And so a relatively light star. Eventually, if you think about the fate of the universe, it's a little bit unclear what will happen. Since the universe is expanding, this can continue forever, right? And the universe becomes less dense and dense, and eventually everything would fall apart. So that the fate of the universe is not such a pleasant one. Unfortunately, it's very far away. And so, you know, the fate of the sun, sorry, there was some echo. The fate of the sun is part of the fate of the universe, but it's not, it's you know, in the end, it's the same, because in the end, the fate of the universe is the fate of everything in it, including the sun, right? And so, if you think about the fate of the universe, there's a lot of research about this. I talked about Alexander Friedman early on in the lecture, and he has made an equation from which you can derive what could happen to the universe. And the different scenarios. Currently, the thinking is that the universe will slowly expand until it, you know, it becomes very cool and very cold, and everything has fallen apart. Does that make sense? Or again?
Yeah, but, I mean, if you look at the sun itself, you know, I mean, it's in our, you know, presence. The sun itself, it's about 4 some billion years, and it will take like maybe the same, around 4 billion years to go away. But the universe is expanding as well.
Yes.
So, and the sun is not at the center of the universe, is that right? So the universe is not built around the sun. We are just maybe in the,
the sun is
left of the universe, so are away from all this expansion. We are in the southeast. I don't know if this is right, maybe not right. Southeast of the universe, and the universe expanding, you know, in all directions. Is that right? So if the sun by itself is gone, which will be gone by then, then, but the universe could be still there because there is maybe more suns somewhere. Is that right?
Yes, the sun could, the sun will cease to exist at some point. And at that time, there will still be many other stars that are made. But eventually the thinking is that all of the stars would disappear. But we're not fully sure of that. You know, there are also theories where eventually everything contracts back to a single point again. And so this depends really on the properties of of the universe. But currently the thinking is that it will keep on expanding. And so once the sun is gone, there will be many other stars and planets and etc. But eventually they will also disappear.
Yeah, but our solar system by itself, maybe it will disappear by itself.
Well,
the entire, you know, the universe. So the universe still maybe will be existing while our small, you know, solar system maybe will disappear because it's run around the sun.
Yes,
which is
our solar system will cease to exist prior to the universe. You know, the ultimate fate of the universe. I have a very nice video about this, which I showed to the students in a class. Maybe we can share that link. It talks about the fate of the universe, and it's a very interesting video. I can put it in my slides, or maybe Anna can send it around.
Yeah, this will be a little bit interesting, you know, to make some interesting, you know, discussion with our students actually.
Yeah, that is I have a very nice video about it. I'm certainly not an expert on it. I'm not, you know.
Okay, maybe one time you can show it for us.
Yeah.
Thank you.
Very good. Any other questions?
How you doing?
Life, the universe, and everything.
How you doing, doctor? Hello, can y'all hear me?
Sorry?
Can y'all hear me?
Yeah, yes, I hear you.
How y'all doing? Thank you for the presentation. Can you, this is a question for any of the academias, but can y'all tell me what y'all know about dark energy and how it affects the expansion of our universe?
Oh, that's a very good question. I did not cover that in here. I thought about mentioning it here, but there was so much material, so I was worried it was too much. So it's very interesting that, you know, of all the things I've talked about, it's only a fraction of the matter that we know needs to exist. And so there are other things like dark matter and dark energy. And for dark matter, we have some evidence that it exists. It's called dark matter because we don't know what it is really. And so we call it, we give it that name. And then there is dark energy, which you're right, has an effect on the eventual fate of the universe because it's a large amount of energy that must be somewhere, but we don't know where. And actually, we know a little bit more about dark matter than about dark energy. But there's still a lot unknown. So for example, there are experiments ongoing, which I did not mention at all, where people try to find evidence for dark matter. And as I said, there is some evidence for dark matter. Dark energy is much more difficult, and there's not any evidence for it really, except indirectly. And it's partially because of the eventual fate of the universe. So yeah, these are very interesting research topics. Maybe in one of the later lectures we'll get back to it. I don't know if any of the other people plan to talk about dark matter or dark energy, but it's an active field of research. And there are certainly groups that are trying to perform experiments about to detect dark matter. It's actually quite interesting because some of the detectors that are used for that research are also useful for the research that we do at the cyclotron laboratory. For example, we're working with a group from MIT on a detector that they put in a balloon and they bring it up into the sky, and they try to find evidence for dark matter. And so we are using the same detector for some of the experiments here, so it's quite interesting. Yeah, that's a very good question.
Thank you.
Any other questions? I guess not.
There's one in the chat.
Ah, I didn't see it. Remco,
I have a question.
Oh, yes, let's do the live one first. Or is that the same?
Can I ask a question?
Yes, please.
So I saw when I visited you, you showed me the experiment. So of course, maybe difficult to answer my question, but what kind of stage of the universe are you experimenting? Like 1 second or 10 years later after the Big Bang?
Oh, you mean me personally?
Or in general, or what's
Okay.
one of the topics?
Yeah, I think, well, there's different areas. So when we do nuclear astrophysics and we do nuclear physics experiments at EFRIB and NSCL, these typically involve heavier nuclei. So these are nuclei that are found in stars like core collapse supernova, or that are created in neutron star mergers. So these are relatively recent, right? Because the stars that form supernova don't last that long. They're so heavy, so they burn to their fuel pretty quickly. So these are relatively recent. But there are also experiments where people try to figure out properties of elements that are much lighter, and these would be created, say, in the Big Bang nucleosynthesis. And so that would be much older, much earlier in the universe. But for these lighter systems, much more is already known than for the heavier systems. So most of the research is currently focused on heavier nuclei, which typically means younger stars compared to the age of the universe. And so, for example, the research I do relates most strongly to core collapse supernovae, which I discussed a little bit. And so these are heavy stars, so they don't live for that long, and so they're relatively young as well.
Thank you. So can I ask a very kind of stupid question? So
there's no stupid question, so go ahead.
Anyway, so we heard that the neutrons and neutron merger create gold and platinum. So in your experiment, can you make us those metals?
Yeah, we can make. I'm not 100% sure I understood the question, but I think, yeah, we can make all kinds of nuclei, and depending on the experimental conditions, we can also create them as very hot nuclei. For example, if we make a reaction of heavy ions and we bombard them on each other, then you can make very compressed and dense nuclear matter, relatively dense nuclear matter, and it's very hot. And so people try to understand some of the properties of nuclear matter itself. This is important, for example, for these neutron stars that I was talking about. It's a very dense material, and so people try to understand the properties of that material, and they do experiments by colliding heavy nuclei on each other. But we can do experiments with almost any nucleus we want, at least when we have EFRIB, right? Because we can produce all these nuclei, and so yeah, we can make anything.
Thank you. Very interesting.
Well, I could add to that. When you collide nuclei to study dense matter, you make it hot. But we can use neutron stars indirectly to probe cold dense matter. And we're actually starting in about an hour an experiment to understand cold neutron stars and how they even get colder. So we can study some of the nuclear processes in a dense environment, even though we don't technically create exactly that dense environment. We can sort of restage some of the nuclear physics.
Great, thank you.
Anybody else? Okay. Okay, so this will be recorded, and I understand this may also be used for follow-up in various classes at the various institutions. The lecturers and everybody else involved will certainly continue to be available to answer any follow-up questions. Okay, so well, let's thank Remco for the nice lecture by finding the clap your hand button, which actually I don't have, right? Oh no, I have it.
It's in the bottom on reactions,
If
like
you,
that. Let me just add one thing. The slides from the lecture will be posted within a couple days in the website, which I just posted on the chat, and the recorded lecture will also be posted as soon as possible. And the second lecture by JINA-CEE June will be on a date to be determined, but on the week of September 21st to the 25th. So stay tuned.
okay. Bye, everybody. I hope to see you back in a few weeks.